everyone's doing good today. So after today, we will have uh, one last meeting on Tuesday, May 26th at the normal time. Next week is technically a normal week of classes, but we never really fell behind, so um, we'll just do what we normally would have done, which is one last activity together. So um, there are also points attached to that activity, so just please be aware of that. Um, and that activity will be due May 29th, which I showed you on Tuesday. That shows on the schedule. Anyway, so where we're at today is we already finished the lab, so I want to give you some help in terms of how to use these parts to build your fourth project. So if you look on my screen, uh, what you will see is I just made a folder for today, but I assembled the parts that I need to work on the project. I'd already done a small example, so you may remember at a point I did have this file reading, which you have, but I also I talked a little bit about creating the tree instance, deleting a tree instance, and then finding an element in a tree. So that part's already done, and I'm just going to add to that example today. I also talked about how you can make your own input file so that you can test your binary search tree. But notice here on the left, I now have the binary search tree, which was completed at Lab 15. So if you've done through Lab 15, you already have the complete binary search tree. I also have word.h, which was provided as part of Lab 16. And then I have word.cpp, which I implemented, we implemented together on Tuesday this week, May 19th. So Word is ready to go, binary search tree is ready to go, and like I drew pictures on Tuesday, the binary search tree is going to be creating nodes to store Word objects. And I'll draw more pictures, and those are harder. Oh, look, I'm still using Jordan's binary search tree, so she's good to go when it comes to the binary search tree part. Okay, so I'm going to start just by talking about inserting something into the tree. So I'm going to change my input. Actually, I'm going to need extras, so let's go look at what the commands are real quick. Get the browser up. Let's go look at what commands are available to us. Because for testing purposes, it's helpful if we print. So let's go look at the operations. In order print is O. So I want to add an O to my output file. So here's what I want, my input file rather. So I'm going to change this so I know that I have to create a tree, and then I'm going to insert apple, and then I'm going to print in order. The big star of the show here is insert, to give you a sense of how you're supposed to use the word and the tree together. This in order print is so that we can see if the insert worked. Does the tree actually have apple in it when I'm done? So there's my input file. Just 3 commands right now. 2 comments, which your file reading should handle already. So we create a tree, we insert apple, and then we print it in order, which should show us apple plus account. Okay, so now let's go to the driver. I'm going to move that to the side. So I need to add myself some commands. I've already got create is already done. Checks for a null pointer, and if the tree is not null, then it deletes the current tree. Then it makes a brand new tree and then prints tree created. Alright, so there's the delete operation that's complete. If tree is null, then must create tree instance. Otherwise, we delete null and say we deleted. Here's the find operation. which is a little bit more elaborate. Has to check to see if there is even a tree in existence. And if that passes, then it will check to see if the tree is empty or not. And if the tree is not empty, then it goes ahead and looks to see if it can find something. So we're going to add a case I to do an insert. So this is the one that probably for most people is the most confusing. I'm also going to go review what the output is supposed to be for insert. So insert, so word will be a string like apple into the tree. So now I'm going to go back and I'm going to look at the outputs file. Here's the insert stuff. Okay, so insert is tricky because we don't allow duplicates. So when we're inserting into the tree, if we find a duplicate, we have to do something different, which is what these outputs are talking about. We still, by the way, have to check to make sure that there is in fact a tree that can be inserted into. Okay, so here we are in the insert. So if tree equals null pointer, then we will output must create tree instance per the instructions. Now we're going to do an else part. Okay, so this is where now we'll start to see the word come into play. And in fact, we're going to have to go fix find because the word is now in play. And in fact, let's go all the way up. Yeah, so the tree right now is a tree of strings. And we need it to be tree of word. So we're going to use our word class. We're going to make a tree where every node has a word class object in it. Not just a string, but a word object. And a word object, if you remember from the lab, has a string and a counter inside of it. So there's still a string in there, but there's also a counter in there. To have access to word, we're going to have to include its header file. So I'm going to go up here way at the top and include word.h. So I get that header from lab 16 available in my project. So now I can use the word class. And yes, the file name is all lowercase, but the class name for word is big W word. So I need to change my tree to work with words, not strings. Now, we might as well, as we work our way back down, fix places where we have references to strings. In case C is an example, we're trying to make a new tree of string, but we don't have a tree of string anymore. We have a tree of word objects. So we will fix that. Delete doesn't have anything that needs fixing. Find does. So right here, we're trying to find a string, but what we need to be finding is a word. So we actually need to update this code and add a word. So we're going to make a word instance called W, and we're going to construct it with the string that we get from the command file. So if the string is apple, then we're going to construct a word instance called W with apple inside of it, which will be automatically converted to all uppercase if you remember the lab. This W also will be initialized with a count of 1. I'll draw a picture of it. Well, let's go look at the code. So when I create a word this way, what happens? Let's go look at word. Word.cpp will have it. So here's the constructor for word that takes a string. It initializes the little w word with the uppercase form of the parameter, and it initializes the count as 1. So this is a lot of moving parts. It's intimidating to keep straight in your head, but The tree is now word object, so I have to be careful here to use word objects as what the tree manages. So here I'm creating the word W that has whatever the string coming from the file is. In our example, it will be apple. So it's going to construct a word. In fact, I'll just draw it. It's going to construct this word. So this is big W word W. Inside, the little w word will be uppercased to apple. And the count will be 1. That's what I just built in my driver. That's this right here, that picture. Okay, so when I go to try to find things in the tree, I'm not finding strings, I'm finding word objects. W. So I'm trying to find a W, something that matches this word that has the string apple inside of it. So I'm trying to find W. And if I can find a node that has a word object like that in it, then my result will be true, and I'll print out, hey, I did find a place where apple exists, or I couldn't find apple. All right, so there's the find updated. So now we're in insert, and we have to think, okay, what we're inserting is not strings, it's not integers, it is word objects. So we need to make a word object. And fortunately, we're going to make it in the same way that we did before. We'll take the command string, and we will just take the text off of it. This starts at character 2, so it'll be I, position 0, space, position 1, and then whatever the word is, position 2. So in this case, if we take substring starting at index 2, that takes starting at index 2 all the way to the end. So in other words, the whole word apple. So now we've created a word object, just like this picture here, with the word apple uppercased in it and the count of 1. So now we try to insert it. And we're inserting words, word objects, not strings, because the tree has word objects in it. So if we can insert, then what was the text again? I gotta go look at the text. The text is word W inserted. Okay. So there's that string again. Our user, by the way, they don't know you sort of imagine that you have some person that just is making these command files. They don't really know what the structure of the code is, so they don't know that what we actually did is made an object of it that has a counter and a string. All they know is, okay, I got apple. It's in the tree. Great. Okay, now why would this fail is the second part. Why would an insert fail? The only reason why an insert would fail is if there's a duplicate piece of data. So this is sort of going back to lab 14. The only reason why a tree would refuse to insert something is because it already had that thing in it. So the tree's going to fail here if it already finds that there's a node with the string apple inside of it. So in that case, this refers back to, and maybe I should draw a picture again, so that you know what I'm talking about, but I drew this picture on Tuesday as well. Okay, so what's this other thing mean? So if I have a tree, and I'll put the insert call over here. So I want to insert a word object built to hold the string apple. What happens to the tree? And I know I have trouble figuring out how big these need to be. And I don't want them too big because then my picture's going to get messy. The first insert is going to take that word object and it's going to put it in here. And we know that the word object in the meantime uppercased everything and it has a count of 1. So that's fine. Now if we were to insert banana, then since banana comes after apple, banana would end up being down here. Be a word object, but inside of it would be the little w word, the string, and the word class will have uppercased that in the meantime and set it to have a count of 1. So far so good. But now what happens if I try to insert apple again? Well, the problem is that what's going to happen is it's going to find that it already has a node with a word object in it, with the string apple inside, and it will refuse to insert it. But that's what the counter's for, as we talked about on Tuesday. So if this insert fails, our next task is to get ourselves a reference to this word object and update this counter. That's what we want to do. If we can't insert it as a brand new node, that means that apple is in here, but we want to increment its counter to show that we've seen it more than once. So this is different than what we've done before. But our tree will actually be aware, or at least have the data inside of it that shows that you tried to insert apple twice. And it won't have created a node for that, but the counter will show that apple was seen twice. So here's how that's going to work. Let's go look at, so how do we do that? Let's go look at the tree. So we need to use the tree's capabilities to grab a reference to that node, and that is what this function is about. If we give it a word object that exists in the tree, it will actually return a pointer to that word object. So in code, in our driver, that's going to look like this. We need a pointer. I'll call it P for pointer. PW, how about? Pointer word. So this same W. So it's going to get the node that has the matching string inside of it and give me a pointer to it. Now in my picture, what that looks like is I'm going to get this. A pointer not to the node. This tree get function gives me a pointer not to the node, but to the thing inside of it. So PW now is this pointer right here that's to the word object inside of some node in the tree. Now I know that this has to work because I was unable to insert W, which means W has to already be there, so then I need to get W. And the reason why I'm doing that is because I want to, where's the word class again? So this is a pointer to a word, and I want to bump up the counter. And we have a function for that called increment count. So that's what I'm going to do. I'm going to take that pointer and I'm going to increment the count on it. So pointer dereferenced, increment the count, which does count plus plus. And now the data is there that you tried to insert apple twice. There's only one apple node, but the counter shows that you've seen the word twice. And then we have an output here that's supposed to be, what is it? word W incremented. So I hope that that's making a little bit of sense. Probably if you're like me when I was uh, sort of at the same stage in my development as you are, I kind of understood it at a high level, but pulling the code together is quite difficult. Okay, so that's what that looks like. Now at the moment, now we're about to go compile this and see it. At the moment, we're only inserting apple once. So we should see tree created, word apple inserted, and then we should see apple be output. And then we're going to talk a little bit about overloaded operators. So let's go compile that. Make sure, by the way, you compile all the CPP stuff. So I'm going to compile the driver. I had to compile word, the CPP stuff. I will just call it p4.exe for now. Should go pretty quick unless I've made a mistake somewhere. I think I hard-coded the input file in here, which your project should not do, but I believe that I hard-coded. I did. And I left a note here that your program needs to be fancy, but in the interest of focusing on what's important for now, I hard-coded the input file in here. Okay, so let's see if it works. Oh, because I didn't do the command O, but it did do the word apple inserted, so that's good. Tree created as expected. Word apple inserted as expected. It didn't handle the command O because I didn't write the code for that. So let's put case O in there. Still have to check for the null tree. But otherwise, it is safe to tree. What was it called? What's that function called? I got to bring up the tree to remind myself. Tree. Print in order. Print in order. Unfortunately, I got to recompile it because I changed the code. If you just change the commands, by the way, you don't have to recompile anything, which I'll show you in a second. So, got to recompile because of that change to the source code. So there it is. Now, hopefully what you're saying to yourself is, why does it say Apple 1? Where did that come from? And we're going to have to do some detective work to find that out. But let's do a little bit of input testing before we do that. So I'm going to go to my input file. I'm going to print in order. Now I'm going to do another insert right after that of Apple again. And in fact, let's just try to capitalize it because it's supposed to be case insensitive. And then do another print in order and see what happens. Do not need to recompile because we did not change code, we just changed the input file text. So this is what we expected and wanted. So it created the tree, that's the C. The first insert of Apple created a word object with a counter of 1. The second insert triggered the incrementing logic, and notice that when the data from the tree prints this time, the apple's counter is 2, which is exactly what we expected to see. By the way, it also, notice inside of the code it was case insensitive, so it didn't care if Apple was all little letters or capitalized, it didn't care. Okay, so yeah. Yeah, so the question, can you just keep adding things to your input? Yes. Because your code just reads the entire file, so whatever it finds in the file, it just reads it, so you can add whatever you want. This is how we test your programs, is I just make a giant one of these with all kinds of weird situations in it to see if your code breaks or not. Um, but yeah, you can keep doing it. We could insert a banana. We could insert banana twice, by the way, or 3 times, and then print an order again. And remember, I didn't change code, so my my program is going to read that file and it's going to spit stuff out. But it's going to read the whole file every time, so it'll just do it. So there's the apple, there's the second apple, there's the first banana. The second banana causes an increment. The third banana causes an increment. And then notice when it prints all the nodes in order, it has the apple with the counter of 2 and the banana counter of 3. It's pretty cool, I think. Um, but yeah, your job is to construct input files to try to expose bugs, which is exactly what I do. So the the grader and I put together files that have hundreds of these commands in them, trying to cause errors in your code. And usually we put these commands in an order that we think might cause errors in your code. Okay, so now I want to go back to, I'll start with this printing. Now, don't do this part. Um, I'm about to cause errors on purpose because I want to sort of explain, like, how the hell does this happen? Where in the tree, when I say print in order, and then I go down to the private print in order, here's the private one. What about any of this says a string and a counter? What about any of it says a string and a counter? If you know this, then you're in good shape. But if you don't, we're about to explain it by causing an error on purpose. So don't do this part, but let me go mess up my Word class for a second. So I'm going to take this friend out of Word.h, and I'm also going to comment it, not delete it, but comment it out of Word.cpp so that you'll see the error. Now I do have to recompile because okay, so I made these errors happen on purpose. It is very hard to read, but the ones we're looking for are so here's a reference to operator that. Here's another reference to operator that. You may notice, by the way, like this same complaint over and over and over again. Line 170, I don't know what to do. Line 170, I don't know what to do. Line 170, I don't know what to do. Over and over and over again. It's probably more of them. Here's another one. Line 170, I don't know what to do. Okay, so this is as a means of trying to explain to you why sometimes we have to have overloaded operators. So this reference to BS tree line 170, let's go look at that real quick. BS tree line 170. I'm guessing that my editor is messed up for you a little bit. I don't, no. Let me squish it down again. Okay. BS tree line 170. Over and over and over again, it's complaining about this line right here when I made that change. So here's what's happening. You have to ask yourself, what is the data of the root node of my binary search tree? I'm going to bring my picture back. The data is a Word object. So what this code is actually saying is, I want to print out, using this operator, the insertion operator, the less than, I want to print out the node's data using this operator. Now the node's data is a Word object, and the error I'm getting is saying I don't know what that operator means for the Word class. Here it is right here, type Word. So what it's saying is I don't actually know what that means for a Word object. So how do we fix that? Well, we go to the Word class and we define that capability for it. So we say with this friend function, this is what it means for a Word object to be printed out on this. And then in the word.cpp file, same thing. Here's the implementation. So what does it mean when Word is the data on that operator? Well, what it means is print out the little w word, which for our example would be apple or banana, followed by a space, followed by a 1. So that's pretty wild that it works that way. But the tree is trying to call that operator on Word, and C++ discovers, oh, Word has that operator. Here it is. What do I do? Well, I put the string and a space and a count. So I will recompile that now with it cleared up. It'll compile now, and then when I run it, and it does that in order print, it's the Word class that's actually informing C++ that it should print out the string and the counter. And that's entirely because we overloaded that operator. I'm going to do one more just so you know why these things are here. I'm going to take out this greater than right here. So I'm going to take out operator greater than. This is not something you need to do, but I just want to show you. From word.h, and then in word.cpp, I'm going to comment out the greater than, and then I'm going to try to compile. Okay, so all kinds of errors. You're going to see the same thing. It's mad on line 160. It's mad on line 160. It's somewhere mad on line 160. So what about line 160 is making it mad in bstree.h? Well, line 160 has this piece of code. So what this piece of code is doing is it's attempting to compare one piece of node data to another piece of node data. So then you ask yourself, well, what in this case is the node data? The node data is words. So what it's actually trying to do is apply this greater than operator to a target word and a data word. But I've commented it out, so C++ says, I don't know how to do that. I don't know what greater than means for words, which is why we have the operator in here. So this tells C++, whenever you need a greater than on word objects, this is what you do. And then I'll just show you where else that appears. If you look in bstree, we also have, let's see, where is it? Here's two words with a less than, two words with a greater than. We have a word being print on the output. Here's another place where we have a word being printed on the output. So that's why we made all of those overloaded operators. Now I'm not sure if we ever used the double equals, but I had you do it to practice it. So we use greater than, less than in a whole bunch of places. I don't think we ever actually used the double equals, so technically it wasn't needed. But the reason why we overloaded these operators for the word class is because if we didn't, I couldn't put word objects in my binary search tree, because the binary search tree requires the ability to compare its data and to print out its data. So because the data is my word class, I had to make sure that the tree could use those operators on it. So that's a lot to take in, but that's why all that stuff is there. We didn't actually end up using the double equals anywhere, but it's good practice. Then if you look, by the way, all these are really doing, the comparisons, is looking at the two strings. So it's completely, it doesn't care about the counter. When it's comparing two word objects, it's really just looking at the two string pieces. Okay, I think that's the hard one. I'll go look. Get the camera off, get the browser back. I believe that's the only places where there's like hard ones that typically people might need help. Find, removed. Well, we could do a got. We'll do the got. And this one says the word in the count. So let's do the got. And hold on, I gotta go off and deal with the thing off to the side here for a sec. I want to see what I expect for got. Yeah, okay. So I'll help you with the got, and then that's sort of my last thing, and then I can field. But let's do the got, which is the G and a string. So we're gonna go to the driver, and let's do the got. I'll do it. I'll just keep going. Doesn't really matter the order. So the got command. Got to check to make sure the trees, there is a tree to look around at. Okay, so a get is, we've already done one of these actually. We're just getting a pointer. So get, oh, we need a word to get though. So we construct a word object here in our driver using the text. Then we get a pointer into the tree itself, which tells us if there actually is a node that contains that data. Then hopefully you know this part. If we get a null pointer back, that means it's not there. So this else part means it's a non-empty tree. This null means whatever you were looking for, it's not in there. And the text we're supposed to say is W not found. Okay, so but if it's non-null, then we can do cout got, and then notice what I'm going to do here is I am going to dereference my pointer and print out the node that's actually in the tree. So I can actually use the pointer into the node in the tree, which will tell me what the word is and what the current count is on the output. So now we need to go to our input file and do a got in here. Let's do a couple of gots at the bottom. So we'll do a get. Apple seems obvious. We'll do a get cherry, which should be not found. We'll do a get banana, which should be found. So in the meantime, I did change the code. I hope I put everything back. I did. I also updated the input file, so when I run this now, let's see if it did it. So there's got apple with the count because I used a pointer to the word object in the tree. Cherry was not found, and then I did the I gotta use the pointer to the node that had this word in its count in the tree and printed it from there. So my hope is that this leaves you time. You have till Sunday, like we've been doing since spring break, to finish. So what you need to endeavor to do if you get to the point where you're finished is test. So I'm in the wrong place. I need to be this browser. You need to test because what I've given you is a sample input file, but it's just a sample. We have others. So we put these together to test your code. So you could do the same thing. The sample output just tells you what your code should print with my sample input, but if you do your own input, then you're going to get different outputs, of course. Okay, so that is it for me. I'll wait for a couple minutes and see if any of you has any questions. Hopefully that's enough. I basically wrote the driver. There's a lot of the driver has already been done in here. But that means that you can endeavor to get a perfect project. Thanks, Jack. See you next week. Yeah, so everybody, regular meeting on Tuesday next week at 11 a.m., which is likely to be our last meeting for the semester. We'll do the final lab.